In section 3, we're talking about continuity. Now, your previous definition of a continuous function is when you can draw something without picking up your pencil. That's a very, very simple way of stating what it is. All right, now, if you look at the pictures of the blue graphs, you can see that the first one and the second one, well, the first one is continuous, okay? The second one has a hole. The third one has a hole. The fourth one is just a jump, okay? So if there's a jump or there's a hole, or if they don't touch and are defined there, then it's not continuous. So there are three possible reasons a function could be discontinuous. That's a removable discontinuity, which is a hole, a jump, and an asymptote, a vertical asymptote. So here's an example. It's a very simple example, all right? I'm just going to make this very, very easy. So there's an open circle right there, and say there's your graph, right? It doesn't have to be perfect, but that open circle is a removable discontinuity, okay? And that could be defined somewhere else, or it could not be defined. A jump discontinuity is like in our piecewise functions, right, that we've seen. So something where it's defined, see, no. Something where it's defined, so there's a point here, and it goes like that, and then there's a circle here, and it goes like that. So because it jumps from one thing to another, that's a jump discontinuity. A vertical asymptote is like what you'd see in a rational function. So say that here's our vertical asymptote, it goes like this, and like this. Right, so that's a vertical asymptote, so that's a removable discontinuity where x is 1. So there is a formal definition. A function is continuous if the following three conditions are met. And this is really talking about a particular point. So if it's continuous at every point, then it's a continuous function everywhere. F of c has to be defined. So it's in the domain. The limit exists, and the limit is equal to the point. So in other words, remember, the limit can exist and just have an open circle there, like in the removable discontinuity. In order for the function to be continuous, that open circle would have to be filled in. Okay? If it's not filled in, it's not continuous. Right? That's not possible. If the limit doesn't exist, that means you have a jump discontinuity or an asymptote where they don't come together anyway. So it doesn't matter if it's defined or not, but if it's not defined, then it's definitely not continuous. Okay? So keep that in mind. If any one of these three conditions is not satisfied, then it is discontinuous. So here's a bunch of examples of continuity. This might be a little bit long, sorry. All right, part A. First, is it defined at this x value? No, there's an asymptote. So the answer is no, because f of -1 is undefined. Simple as that. So in order to show continuity, we're going to go through all three steps. If it doesn't work with one of them, then the answer is no. If it works with all of them, then the answer would be yes. So it's a slightly arduous process. So let's look at part B. We're worried about what's happening when x equals 0. So f of 0 is 3. Okay, that's not too bad, right? That's a closed point. Does the limit exist? The limit as x approaches 0 of f of x is also 3. Okay. We know that because from the left it gets to 3 and from the right it gets to 3. All right, the limit as x approaches 0 of f of x is equal to f of 0. Therefore, now remember, I don't know if you saw this in geometry, but the little three dots that make a little triangle is the same thing as saying therefore. It is continuous. At x equals 3. All right, for part C, we're looking at -1. So is it defined? Yes, it's defined right there. f of negative 1 is 2. The limit as x approaches negative 1 of f of x, according to this, if this is going to 2 and this is going to 1, that would not exist, right? Like we talked about in section 2. So that means, therefore, not continuous at x equals negative 1. And that's really all we're worried about because that's all it's asking for. All right, part D. In order to determine where f of 1 would be, right, because we're worried about what's happening at 1, we just plug in 1, so we get 3 minus 5 plus 4, which ends up being 2. The limit, well, because when we plugged it in, we got 2, and there's no issue, there's no removable discontinuity, there's no asymptotes, we don't have to worry about that, then the limit as x approaches 1 of f of x is also 2. And so since the limit as x approaches 1 of f of 1 of f of x is equal to f of 1, it is continuous at x equals 1. Let's look at E. Well, if it's 2, then 2 squared minus 4 is 0. That means the denominator is 0, which means G, this is G, of 2 is undefined. Therefore, G is not continuous at x equals 2. Right, so if it's not defined there, it actually makes it easier, makes it a little bit faster. All right, for f, it's asking for 3 different numbers. Well, let's see, if we have negative 2 and 2, those are pretty easy to rule out. Okay, so it's not continuous at x equals negative 2 and 2. We know that because the denominator would equal 0. So let's find f of 0. Well, that means we get the square root of 2 over negative 4, which means the limit is also the square root of negative 2 over 4. So because they're the same, it is continuous. Negative root 2. Oops. It's not continuous there. It's continuous at 0, because that's what we got when we plugged in 0. Now for G, we're really only worried about 3, right? Because that's what it says. So in order to do this, the first thing I'm going to do is take that first equation and simplify it. Also, this is a typo. That should be greater than. It should be correct on your paper. So I'm going to take that top equation and factor it, right? Because it's x squared minus 9 over x minus 3. So that becomes x plus 3, x minus 3, over x minus 3, which means it's really just x plus 3. So I'm going to use that when I find the limit. Now, it says that when x equals 3, the answer is 9, which means f of 3 is 9. It is defined. Okay, that's good. Now let's find the limit. Now, because it's a piecewise function and it's surrounding 3, that's where it switches from one to another, we're going to have to find the left-hand limit and the right-hand limit. So the left-hand limit is a limit as x approaches 3 from the left of f of x is this x plus 3 equation right here. So it'd be 3 plus 3, which is 6. Then I'll plug it into the right, so the limit as x approaches 3 from the right of f of x, which is the bottom equation down here, which is 3 squared minus 3. Well, 3 squared is 9, minus 3 is 6. So the limit exists, but the limit as x approaches 3 of f of x is 6, which means that this, the 9, does not equal 6, which means it is not continuous at x equals 3.